In each of 3 through 15, a sequence is defined recursively. Use iteration to guess an explicit formula for the sequence. Use formulas from section 5.2 to simplify your answers whenever possible. C sub k equals 3 times c sub k minus 1 plus 1 for each integer k greater than or equal to 2, and c sub 1 equals 1. Now, iteration is my favorite way of solving recurrence relations. Basically, the way this works is we're going to calculate c sub 2 and c sub 3 and c sub 4 and so on, but we're not going to plug in our initial condition here, that c sub 1 equals 1. We're going to write each term in terms of c sub 1. So, for example, c sub 2, according to the recursive definition, is going to be 3 times c sub 1 plus 1. But I'm going to leave it like that. I'm not going to plug in 1 into that c sub 1. I'm just going to leave it like this. Now let's go to c sub 3. C sub 3, according to the recursive definition, is 3 times c sub 2 plus 1. But we want c sub 3 in terms of c sub 1, so we're going to take this expression and substitute that into c sub 2 to get 3 times c sub 1 plus 1. Now I'm going to distribute this 3. But instead of writing 3 times 3 equals 9, I'm going to write it as 3 squared. So I'm sort of combining factors of 3. So what I mean by that is we should write our solution as 3 squared times c sub 1 plus 3 plus 1. Now let's move on to c sub 4. According to the recursive definition, this is 3 times c sub 3 plus 1. We can then substitute our solution for c sub 3 into c sub 3 here to get 3 times 3 squared times c sub 1 plus 3 plus 1 plus 1. But again, I'm not going to multiply 3 times 9 to get 27. I'm just going to write it as 3 cubed times c sub 1 and then plus 3 squared, then plus 3 plus 1. The reason why we combine factors like this is so that it makes it easier to identify what the pattern is. If you notice, these are just powers of 3 here. And if you notice, the largest power of 3 is always one value smaller than the index. So if we were to generalize this, we would say that c sub n equals 3 to the n minus 1 times c sub 1. And then we have a series of all of the smaller powers of 3. So we would have 3 to the n minus 2 next, and then 3 to the n minus 3. And so on until we get to 3 squared plus 3 to the 1th power, that's just 3. And then this plus 1 can be written as 3 to the 0th power. So now we have an explicit formula for c sub n. Now we can plug in c sub 1 equals 1 into c sub 1 here to get that c sub n equals 3 to the n minus 1 plus 3 to the n minus 2, and so on until we get to 3 squared plus 3 to the 1th power plus 3 to the 0th power. Now, this is a series, a very special type of series. This is called a geometric series. And just to show that it's a geometric series, I'll write this in sigma notation. If we start at I equals 1 and go to n, then we have to ensure that the exponents start at 0 and end at n minus 1. So this will be 3 to the I minus 1th power. So the first term in the series would be 3 to the 0th power, and the last term in the series would be 3 to the n minus 1th power. This is a geometric series. Since this is a finite geometric series, there's a formula that we can use to evaluate what the series is. This is just the first term, which in this case is 1, times 1 minus the common ratio to the nth power, which in this case is 3 to the nth power, all over 1 minus r, which is the common ratio, in this case, 3. This simplifies to 1 minus 3 to the n over negative 2, which means we can rewrite our explicit formula here as negative 1/2 plus 1/2 times 3 to the nth power. And that's the explicit formula, and this explicit formula should work for all n greater than or equal to 1. Let's test this, though. If we plug in n equals 1, we get negative 1 plus 3/2, which is 1. If we plug in n equals 2, we get negative 1 plus 9/2, which is 8/2, which is 4. So is the next term of this sequence 4? Sure enough, c sub 2 equals 3 c sub 1 plus 1, which is 4, since c sub 1 equals 1. So it looks like this explicit formula works. Thanks, everyone, and I'll see you in the next video.